Sorry for the inconvenience. I had to stop at 1.2.2 ending because I did not want to take risk of recording being disrupted. We have to talk about memory storage and wide area networking. Memory storage is like how first it just is basic introduction. Actually, I completed a video on the whole thing, but then realized that the bloody recorder, did not even record what I actually wanted it to record. But fine, no problem. So we have here 16 KB to 64 GB of size increase approximately 4 times every 3 years. Memory access times is the same. Hard drive capacity from 260 MB to 250 GB, and then this is in 2004, and then it increased to 3 TB till 2011, and then it has also increased from 3 TB to more than 2 to 3 times till present date also. So see here, the capacity increase about 10 times every 8 years. Gap between processor speed and memory is widening because processor speed increases, but the memory speed lags behind. Disk storage technology, it surpassed 3 TB capacity after 2011. SSD handles 3000 to 1 million write cycles per block. In the sense, what it can last for several years under heavy load, but it won't cause any problem. Power consumption, cooling, packaging constraint limit for the scaling of large systems. Then how clock frequency and have increased. Low voltage should be less. They are saying Jim Gray's code. The unit. This is basically, if you remember, tapes units are dead. Disks are tapes unit. Flashes are disk, and memory is cache. It's just I see tape, disk, flash, memory, and C and M like that. Despite speed, okay, SSD is still expensive compared to stable disk arrays as of 2011. The SSD and the flashing and all are costly. System area interconnects three things: LAN, SAN, NAS. LAN, local area, you know better. Storage area is servers to network storage, like this. See, it connects servers to network storage. Then NAS, see, it's the reverse of SAN. It is network area, not area. Instead of area, you just have to write attached network attached storage. See, simple. Connects clients directly to this. So here you can see client servers to large servers. Okay, client hosts to large servers. Then servers to network storage like disk arrays. So instead of, it's like C to A to B, B to C. So instead of A to B, B to C, it's directly from A to C. It's like that. Okay, network. How these three are combined together. That's the diagram. And then you have wide area networking. How it is increased from 10 Mbps, speed bandwidth speed to 1 Gbps in 1999. From 1999 to 2011, from 40 to 100 Gbps. The rumors are like 1 Gbps, like maybe 2013, but we don't know for now. We can check and research about it. How network band? See, they say network by the research or by the details, the network bandwidth are doubled every year, but in the Moore's law, we saw that instead of network, the processor speed increases every 18 months. So here it's faster than network bandwidth, increases faster than processors thing. Fast networks enable massively distributed system by connecting more computers efficiently. See, IDT reports predicts InfiniBand Ethernet as dominant HPC interconnect host. A figure, it's basically this diagram, and there is one, graph which shows the like this RAM and that thing, not RAM. Growth of DRAM and disk. That's key points. You can see memory capacity increases, but latency and access speed improves. Lag behind. SSD flash memory provides faster storage alternative, but they are also costly. Clusters uses a mix of LAN, SAN, and NAS networks for data storage communication. Wide area networks have improved dramatically. What have they improved? Network bandwidth and all, enabling large scale distribution. What is that? Distributed computing. You can also talk about distributed system where multiple computers are connected together. Virtual machine and virtualization middleware. It's so annoying, to explain something which I already explained, but then realize that it's not actually recorded. Anyways, no problem. 20 minutes were wasted. But what are virtual machines? They solve issues of resource underutilization, software inflexibility, manageability, security. What are dependent on virtualization? See, large clusters, grids, and cloud. They all relied components of VM. Okay, first we'll see what VM is. So you have physical hardware which runs a host OS. Okay, and we have virtual machine which runs on a virtual resources and which is managed by guest OS. Now we have VMM. What is a VMM? It acts as a mediator between this guest OS and the hardware. Okay, for this virtual machine to run properly, you have three virtual machine architecture. Let me just show you. Uh, yeah, or if you can see here, this is a physical machine, normal application. You have three virtual hearts. So here you can see that everything is handled by the hardware itself over here. You don't have the hosting hardware. So in the privilege mode, in non-privilege mode, all the guest application and guest OS are accessed. If you see over here, you have there are no modifications can be done, but it has a host. If you see here, see high performance direct hardware control for native. Hosted runs on top of host OS in non-privilege mode. Simply you have to tell the where VMM, what VMM is doing. You just have to tell about that. VMM runs above host OS in non-privileged mode. Here VMM partially runs in non-privileged mode and privileged mode. You can say here user mode and supervisor mode. So that's it. Here hosted VM easier to deploy, no host OS modification. Here you need host OS modification. Then primitive operations, you have four: multiplexing, suspension, provision, migration. What is multiplexing? It's nothing but a single hardware can you can be used for multiple operations. Like so, see the multiple VMs share the same hardware concurrently. If you see the diagram over here, multiple virtual machines uh, share the same hardware. Okay, for example, in the same hardware, more than three virtual machines are running. Then you have suspension. What happens? Suppose these two are here. Now you want to do suspension. So what you will do? You will stop. You will load this thing over here. Okay, that's what this thing is about. So you saved it in the storage. To save in the storage, to make save to stable storage. Suspended VMs can be resumed on the provision. Now you have this. Now you had this OS in the storage area. Now you are moving this OS, so which you had over here, into the different VM. So suspend VM can either wapas, it can either go here itself to resume the same hardware, or it can go to the next hardware. The example which I had given in the previous recording, which was not actually recorded, was suppose you are dancing in a class rehearsing and you had to stop your rehearsal for the lunch time. Now you can either resume this your rehearsal in the same classroom, or you can choose a different classroom based on like suppose the other class people came to access the room or something like that. Then at the end, suppose you both were here. Now what you can do? Yeah, you can shift these VMs over different hardware. So from here, this thing is going here. See, basically it's just one system. First it goes here, from here it goes here, and then from here to where it goes here. Just like that. Live migration. See here. Oh, can move between hardware platforms transparently. Benefits: flexible resource allocation and portability, improve server utilization, consolidation, multiple functions on fewer physical servers, can increase VVM claims. Server utilization can increase from 5 to 15% up to 60 to 80% via virtualization. Infrastructure, see how physical compute, storage, networking, they all are mapped dynamically to virtual machines hosting applications. They decouple hardware and software, which is increasing efficiency, responsiveness, and cost effectiveness. They also where supports crucial virtualization support is crucial for clusters, grid, and cloud computing. Then data center visualization, you don't have much. You just have to talk about data growth and cost breakdown. Data growth, what from hundreds to thousand has growth. Cost distribution for mostly servers and this, that is IP equipment and chiller cooling things. Take 33%, which is almost 60% of operating cost for managing and maintenance. See, 1 to managing and maintenance. 18% for UPS power backup, 90% of computer room air conditioning. Remember AC of computer room. 7% of distribution lightning transform. Now you can see here electricity and cooling costs increases from 5 to 14% over 15 years. Utility costs overtake hardware over 3 years. Then low cost design. What you have to do, instead of high end switches routers, you have to use commodity switches, and you have to use commodity x86 servers instead of that high servers, because what they do, they are easy to replace and low cost. Then software layer handles network traffic balancing, fault tolerance, and expandability. See here, high switches and this router, they are too expensive for data center and scale. That's why you are using commodity switches. Then convergence of technology enabling cloud computing. You have to remember these four things, which are also mentioned in the here over here. If you see convergence, 1, 2, 3, 4, same thing. Hardware virtualization and multi-core chips, utility and grid computing, service-oriented architecture, Web 2.0. So utility computing is for on-scale demand resource, computing resource. This is for drive platform and software innovation, enabling self-efficient management and self-healing operation. Autonomy, the name tells you. You have to remember the heading and write it. Scientific data deluge, and cloud computing. Jim Gray's challenge: how to manage and analyze data review. How we can do, see, data originates from where sensors, labs, simulators, archives, webs. How to manage them: scalable file system, database and algorithms, workflow automations, virtualization tools. Computer Science Telecommunication (CST) Telecommunication Board recommends developing tools for data capture, creation, and analysis. Like you know how you refine your photos. You took the photo from camera, you did some editing and all, or you are creating a new thing in Canva, and then analysis, understanding, and stuff. Cloud computing impacts on e-science. See, it supports data intensive and science, data intensive science and parallel computing. Two things it does. Then it links between computer science and interdisciplinary, it generates for new scientific insights. It provides on-demand services or infrastructure as a service, platform as a service, and software as a service. Infrastructure, platform, software. Map reduce, so which we'll study in the sixth module. What it does, it helps in data parallelism and fault tolerance. What are the programming models? That's it. Then emerging trends, they runs on massive clusters, multi-threading are there, many core GPU clusters are there. They transform architecture design and programming, introduce pipelining. You have some quiz questions over here you can answer. According to 2009 IDC, which is the following accounts for the largest portion of data center operations, see IT and equipment chips. Cloud data transfer, why it takes 86 servers? Because they are low cost and easy to replace. Which is the following technology? Ethernet. Which is the following technology not a contributor for any cost? Quantum computing. Seriously, physics. It's physics. The increase of in which of the following costs have activities and more significant data operations? That is electricity and cooling. This was the data center operations, server purchase cost, software license cost, network hardware cost. It's servers purchase, I guess. Map reduce is primarily used for data parallel processing and fault tolerance. The scientific data delivery refers to rapid growth of science data from various resources. That's it. Which of the following is virtualization in data centers? Increase server utilization and flexibility. The some questions. You will have these notes in the description, and then we'll move to the next topic in the next video.